So today we'll start with mirrors, and we'll specifically the spherical mirrors, or mirrors that are converging, are known as converging or concave, or diverging and convex. When we had a mirror that is plane mirror, like this one here, then we said that the law of reflection is the incident angle is the same as the reflected angle. This is the incident angle, and this is the reflected angle. And those are created with the perpendicular to the surface. With the spherical mirrors, we will use the same thing. But what we will have to keep in mind is that the normal is actually it's the center of the curve. So if we have a converging mirror look like this. And we have a principal axis that goes straight in the middle of it. This is known as the principal axis. We have a point here, which is the center, or the center of the curve. And then the midpoint of it is the focal point. Okay, midpoint. So the distance from center to the focal point and the distance from the focal point to the mirror is the same, is half of the radius of the curvature. Another thing is that we'll use the object. That can be a candle or any object. This is the object, how we represent the object. And then we see the incident ray that is going from the object to the mirror. And then we say that in order to figure out what is the image created, we have to follow some rules. But it is the same angle as the normal. So this is the normal. And the norm, this angle is the same, which is going through the focal point. Oh, sorry, it's a reflected, not incident. It's a reflected ray. So what do you see here is a converging mirror. There are two terms for it, is the converging or concave. Both of them are used in everyday life. And the diverging mirror will look something like this. And we still will have that principal axis, which actually is an imaginary line that goes through the center of the mirror, and through the center of the mirror, and through the center of the mirror, if you understand. So this is the center of the mirror, and this is the center of curvature of the mirror, which makes this the focal point, the mid distance between the center of the mirror and the center of the curvature of the mirror. And then here is where we place the object. So this is principal axis. And here's where we place the object. And the incident ray is, again, if it is going parallel to the principal axis. And this is the normal. From the point where it hits the mirror to the center will be the normal. then it is reflected passing through the focal point. This is a reflected ray. Okay, so what do we see in this case is that as the object is, or the incident ray is hitting the mirror, then a reflected ray is formed, and we see the two cases. The converging was above, and this is a diverging or convex mirrors. Okay, so let's see now what are the rules to figure out what is the image. So the first rule that we will apply will be that the incident ray, if the incident ray is parallel to the principal axis, then will be reflected through the focal point. So this is the first rule. If the incident ray is passing through the focal point, then through the parallel to the principal axis, then will go through the focal point. The second one is that if it goes through the focal point, then will be reflected, rule number 2, then will be reflected parallel to the principal axis. Usually you will have 99% of the cases to figure out that what the image is based on those two rules. However, if this is the third rule, if the incident ray travels passing through the center, then it is reflected back to the center. Whether or not an image is formed depended on the number of factors, like what type of mirror is it, concave or convex, what is the focal length, f, that is the distance between the mirror and the focal point, and what is the distance between the object and the mirror, which is known as DO. Okay, so there are different cases. I will bring some pictures here which demonstrate those rules, and then we will move forward with more calculation. Okay, so here we are dealing with convex mirrors, concaves or concave mirrors. And then we have the principal axis is this one here, and the concave mirror is here. And then we place the object beyond the center and the focal point. Okay, so now the first rule is saying that if the incident ray is parallel to the principal axis, then will be reflected going through the focal point. So if this is the incident ray, this is the reflected ray. And then if it is going through the focal point, so the incident ray is passing through the focal point, it is reflected. This is the reflected ray. It is reflected parallel to the principal axis. Now the third rule is saying that from the center is reflected back to the center. So in this case, we have the incident ray is the same as the reflected ray. Usually with the first two rules, you should be able to figure out what is the image, and the image is this one here, which is smaller than the object, and it is inverted. And since the point of intersection between the lines is a real thing, is not an extension of, then we can say that the image is real. However, when we have this situation here where the object is exactly at the focal point, then we apply the rule. So we see that the incident ray parallel to the principal axis is reflected back to passing through the focal point. And if it is passing through the incident, the center, then it is reflected back to the center. And those two lines are parallel to each other, so there is no image that is formed. The third situation when we see here is that the object is placed exactly at the center, and then we apply the first rule. In incident ray parallel to the principal axis is passing through the focal point, and incident ray passing through the focal point is reflected parallel to the principal axis. And then what we will see is that the image and the object are with the same height. The image is inverted and real. On the case when the object is placed between the focal point and the mirror, what we will see following the rules is that the image is created by extension of the reflected rays, and this makes the object imaginary imaginary image, and it is larger than the object. And on the case when the object is placed between the focal point and the center of the mirror, then applying the rules that we just said, that it's parallel, incident ray parallel to the principal axis is reflected passing through the focal point, and incident ray passing through the focal point is reflected passing parallel to the principal axis, then we will have an inverted image. A real one, because you see that the intersection between the two reflected ray is the same, is not an extension, is the mirror itself. However, when we see this situation, when we are dealing with a diverging mirror, then the object is somewhere here. Here, this is the principal axis. This is the principal axis. And what we are doing again is that we are drawing a line that is parallel to the principal axis. So this is the incident ray, and it is reflected passing through the focal point. And if we are drawing a line that passes through the focal point, this is the incident ray, it is a reflected pass parallel to the principal axis. This is the reflected ray, and the extension between those two lines. And then we have the third rule, which we can easily skip it. And then the image that is created here, this is the image that is created here, is imaginary image, and it is smaller than the object, and it is erect, is on the same direction as the direction of the object. Okay, those are rules so that we apply to figure out what is the image. However, we have equations, and those equations are in your formula sheet, so you don't have to remember them. And mirror equations are as follow. The focal length is half of the curvature of the mirror. And then the other formula is 1 inverse focal length is equal to the inverse of the distance of the object plus the inverse of the distance of the image. So F is focal length. DO is the distance of the object from the object to the mirror. And DI is the distance from the mirror to the image. And then another formula that we use, or that is part of the mirror equations, is that magnification is H of the image over H of the object, or negative distance of the image over distance of the object. So H is the height of the object and the height of the image. Height of image. And another thing that we have to keep in mind in terms of the equations that we have presented here is that it doesn't really matter what are the units for as long as we are using the same units. And this one here is magnification. Okay, so I want to bring something here. In terms of the what do we have in terms of the image and what do we have in terms is in terms of the positive and negative. So you have to keep in mind that if we have a focal length that is positive, then it's considered to be a concave mirror. And if the mirror is convex, then the focal length is negative. The distance of the object is always positive because it is always on the side that make the curved mirror a curved mirror. And if the distance of the image is positive, then we are dealing with the image being on the side where the mirror is. So on the side, which side is the mirror? But if it is negative, then we are talking about a virtual image, an image that in the ray diagram is formed by extension of the reflected rays. The height of the object is always considered to be positive. It doesn't matter if it is drawn down or if it is drawn up, going up. And if the height of the image is positive, then we are dealing with a virtual. And if it is negative, then we are dealing with imaginary, with a real image. Now, the summary is DI is negative, always erect for the imaginary image, and DI is positive and always invert for the real image. Let's see some examples, and then this will kind of make sense more when we are talking about those terms here. So let's suppose that we have an object that is placed 60 centimeters away from the converging mirror. Okay, so as I said, like in those questions and those type of questions in optics, doesn't really matter what are the units. You don't have to convert them into centimeters, but the only thing that is important is to have them in the same units. So now from this information, we can gather that the height of the object is 5 centimeters, and it is placed, since it is placed away from the converging mirror, so will be d of the object will be, it's always positive, 60 centimeters, as we said here, is always positive. The radius is equal to 80 centimeters, which tells us that the focal point is half of the radius, which will be 80 centimeters divided by 2 equals to 40 centimeters. So that f that we have there. Now, since it is a converging mirror, then focal length will be positive 40 centimeters. So now we are looking for the distance of the image. Let's use the equation 1 over f is equal to 1 over dO plus 1 over di. And from here we figure out that 1 over di is equal to 1 over f minus 1 over dO. So 1 over di is 1 over positive 40 minus 1 over 60. And then we will have, after we find this in our calculator, we will have that di is 120 centimeters, and it is positive. Now, this is telling us that the distance of the image is positive. So is the indication that it is on the same side as the mirror, which means that we are dealing with a real object, a real image. Now let's see if it is inverted, or if it is taller or larger than the object. So let's calculate now the based on the fact that magnification is hi over ho, or negative di over do. Let's calculate what is the height of the image, which will be negative di cross multiply 2 that you know, divide by what is left, or do. So this will be negative 120 times 5 centimeters, which is always positive, over 60. So it will be negative 10 centimeters. This is telling us that the image is inverted. So it is a real image and it is inverted. So it's saying this, that if the object is going up, the image will be going down. Or if the object is going down, then the image will go up. It's the opposite direction, opposite orientation. Now, the image is 10 centimeters tall, which means that is larger than the object. Okay, so let's take a look now to another question. And this is a 5. Oh, no, this is the same. Just wait. So now we are dealing with the same object, but now this object is in a diverging mirror. Okay, so diverging mirrors, they look like this. There is a principal axis, and the object will be placed somewhere in here. So the object is placed 60 centimeters away from a diverging mirror with a radius of 80. So the radius focal point is here, and the radius is somewhere in here. or the center is somewhere in here. And the object is between the center and the focal point. The height of the object is 5 centimeters tall. And what is important is just to have everything the same. So all the units the same, doesn't matter. You don't have to convert them into meters. So the height of the object is 5 centimeters. The object is placed 60 centimeters away from the mirror, and those are both always positive. And now we have radius of the mirror as 80 centimeters, which tells us that the focal length will be radius divided by 2, half of it, or 80 centimeters divided by 2 equals to 40. But since we are dealing with a diverging mirror, then the focal length will be negative. We are looking for the distance of the image. So 1 over the distance of the image is equal to 1 over focal length minus 1 over the distance of the object. So 1 over distance of the image will be 1 over negative 40 minus 1 over 60. And then we have here that the distance of the image is a negative 24 centimeters. The fact that we have a negative DI means that we have a virtual image. Virtual imaginary depth. Now let's take a look at the height of the image. So we'll use the fact that magnification is height of the image over height of the object, or negative distance of the image over distance of the object. And from here we'll find the height of the image as distance of the image times height of the object over distance of the object. And this will be positive 2 centimeters, which tells us that the object is in the same direction as the image. They are in the same direction, but they are diminishing. It's smaller. Okay, so we can say that the image, the characteristics of the image is that it is virtual, it is erect, it has the same direction as the object, and it is diminished. Okay, we'll bring another example here, and then this will be done for the mirror. So we have here an erect image of an object is 1/3 of the size of the object. If the object is 20 centimeters from the mirror, what kind of mirror is it? And what is the focal length? Great, so now what we have is that the distance of the image is the third of the distance of the object, okay? Now, however, since the image is erect, that means that it is a negative one. Okay, it's a negative sign. Since the distance of the object is 20 centimeters, then we can say that the distance of the image is negative 20 centimeters divided by 3, which is negative 6.67 centimeters. Okay. Now, on the other hand, what we have is the mirror equation is 1 over f is equal to 1 over di plus 1 over do. Okay, so this will be 1 over f is equal to negative 1 over 6.67 plus 1 over 20, which will be 1 over centimeters, which means that the focal length is negative 10 centimeters. So now that means that the mirror that you are or the problem is presenting here is a convex mirror or a diverging mirror. A virtual image is always larger for a concave. A virtual image is always larger for a concave mirror, and it is always smaller for a convex mirror. Okay. But this is for the mirrors. I will post some practice questions as well so that you can practice on either writing or drawing the ray diagram and using the mirror equations.